Hello, good morning to all of you. My name is Kushal and I'm a assistant professor in Engineering College Bikaner in Mechanical Department. So up to now we have done up to third unit. So today we will start fourth unit. Okay. So fourth unit topic is 2 degrees of freedom. Okay. So as we have already started, let's see. First take example of single degree of freedom. This is example of single degree of freedom. We know that only x of t required, means only one independent coordinate is required to find out the position of this mass. Okay. So what we do earlier, what we have done, we have drawn the free body diagram on the mass, and then we got this equation by applying Newton's second law, and this is the equation. We got one equation because this is 1 degree of freedom. So if there is 2 degree of freedom, we will get 2 equation. Okay. So this is example of 2 degrees of freedom. Okay. x1 and x2 required for all the masses m1 and m2 to determine the displaced position of the masses. Okay. So same here, we will apply Newton's second law. Here one thing we have to assume, x1 is greater than x2. Okay. So if we will apply Newton's second law in this system for m1, this will be elongate this spring. So the force will be on the left direction. x1 is greater than x2. It means this spring will be compressed. If it will be compressed, it will apply the forces in opposite direction. So this force I have shown here and here. Now m2, only one force, k2x2, k2x1 minus x2 I have applied here. So after drawing free body diagram for mass m1, I can write m1 x1 double dot is equals to minus k1 x1 minus k2 x2, because these both have opposite direction. Okay. So finally we will get this equation, m1 x1 double dot plus k1 plus k2 x1 minus k2 x2. Okay. On solving these 3 steps, for mass m2 same we will do, m2 x2 double dot is equals to minus k2 x1 plus k2 x2, k2 x1 plus k2 x2. Okay. So these are equation 1 and 2. Okay. So now we will go further. Now these 2 equations we are trying to get a matrix form. Okay. So I have already made this matrix form. If we multiply this by this, m1 x1 double dot plus k1 k2 x1 minus k2 x2 is equals to 0. This is equation 1. For equation 2, m2 x2 double dot plus minus k2 x1 plus k2 x2. This is equation 2. Okay. So this is matrix form of the equation. So here we can observe this is 2 by 2. This is called a mass matrix and this stiffness matrix. Both are size of 2 into 2. Why 2 into 2? Because it has 2 degree of freedom. Okay. So here size will be determine your degree of freedom. Suppose it is 3 into 3. Then your system is having 3 degree of freedom. Okay. So now let's start with this system. Same we have to do, assuming x1 is greater than x2, applying free body diagram on m1 and m2, check the spring force where it is acting. For mass m1 same, I am applying m1 x1 double dot plus k1 plus k same. Okay. This is equation 1. For m2 I am doing the same. This is very simple, just apply Newton's second law. Now I am assuming that the motions are harmonic and periodic. Let's say x1 of t is equals to a1 sin omega t plus phi and x2 t is equals to a2 sin omega t. Why we are assuming this? Because we know in the previous cases we have done single degree of freedom, and the solution xp of t, that is steady state response, is something like a sin omega t plus alpha or minus alpha. Okay. So in keeping that in my mind, I'm putting this as my solution, I'm assuming. Okay. And then I'm putting this equation in the equation 1 and 2. What I get? Put these 2 in equation 1 and 2. Where are the equation 1? This is equation 1. This is equation 2. We have to put x1 a sin omega t plus phi here, and x2 is equal to a2 sin omega t plus phi here in both the equation. So in one I have put m1 into x1 double dot, that is minus a1 omega square sin omega t plus phi, like this, and I will get this equation. Okay, m1 a1 omega square plus k1 plus ka1 into minus ka2. Okay, same, if I put x1 next to equation 2, I will get this equation. Okay, so now I have equation 3 and equation 4. Okay, now after solving equation 4 and 5, I will get equation 5 and 6. Okay, I will just cancel sin omega t plus phi, all this equation. I will get this equation. I am arranging again this equation 3 and 4. Okay, I have just arranged this, not at all. Okay, so equation 5 and 6 I have arranged. Okay, so this is a1, a2 and a1 and a2. Now we can find that the equation 5 and 6 is algebraic equation. So we can solve this easily. So one way is to solve set determinant 0. Okay, so I have set determinant 0 here. Yeah, a1 or a2 matrix is equals to 0. It means determinants will be 0. Okay, so cross multiplication and then set to 0. On solving we will get this much. Not heavy equation, but yeah, it will be very complex. It will be very complex if you solve it. Okay, so what I will do, for simplification, I am assuming this equation k1 is equals to k2 is equals to k. Okay, assuming m1 is equals to m2 is equals to m. Now the equation will be this. Now it is simplified form and it is quadratic in omega square. Okay, this equation. Now if I solve this quadratic equation, I will get omega 1 is equals to root k by m and omega 2 is equals to 3 k by m. Two values, obviously quadratic equation. So we have now two frequencies. The lower one we call first mode, and then higher one second mode, and then next higher one third mode. Okay, like that. So it is first mode, it is less value. So it is higher value, so it is second mode. Okay, so now we have to find a1 and a2 also, because xt is equals to a sin omega t plus phi. Omega we have find out already, this 1 and 2, and a1 and a2 we have to find out. Then we will find the position of the displaced masses at any point of time. So what I am doing, again I am going for equation 5 and 6. I can write equation 5 and 6 like this. Equation 5 and 6, I have, this is already equation 5, this is 6. I am just equating it to 0. This term will be here, and then a1 by a2. Same for equation 6. So if I put here omega is equal to root k by m and omega is root 3 by km, I will get some values. a1 by a2 is equal to 1. If I put omega is equal to root k by m, a1 by a2 is equal to minus 1 if omega is equal to root 3 k by m. Okay, as I already told you, lowest natural frequency is first mode, and next higher second mode, and so on. So omega is our first mode of vibration. Okay, and that is second mode of vibration. So here one term is important, principal mode of vibration. If the two masses vibrate at the same frequency and are in phase. In phase, what do you mean in phase? Then it is called a principal mode of vibration. What is in phase? I am discussing here. Okay, as I am saying, a1 upon a2 is equals to 1 and omega is equals to, when omega is equals to root k by m, it means two masses moves in the same phase. Okay, telling you by this diagram. Suppose a1 is equals to a2 1. It means either it will move in this direction, means both these masses have the same direction, either right direction or either left direction. a1 by a2 is equals to 1 means both masses have the same direction, either in right direction they will move or either they will move in the left direction. Okay, a1 by a2 minus 1 means they moves in opposite direction but having the same amplitude. Either they will move like this or they will move opposite to each other, away from each other or close to each other. That two conditions are there. So what does this definition says? If the two masses vibrate at the same frequency and are in phase, so this is the case where our A1 by 2 is equal to 1, they are moving in the phase. So this is also our principal mode of vibration when omega is equal to root k by m. Now mode shape. It is the pattern of vibration executed by a mechanical system. Okay. We have find out it is the pattern of vibration executed by mechanical system at a specific frequency. Now my system moving with either of at omega is equal to root k by m or either at omega is equal to root 3k by m. So if a1 by a2 is equal to 1, it means it is moving at root k by m only. Okay. In that case, a1 and a2 have the same value. So now I'm just drawing for sake of understanding. Let's say this is mass m1 and m2. These have the same displacement because a1 by 2 is equal to 1. This is fixed, so displacement will be 0. It is also fixed, displacement will be 0. So this kind of mode shape we will find out. Okay. Up to here linear, increasing linear, constant, and then again linear, decreasing linear. It means the middle spring will neither elongation nor compression. In the diagram you can understand. Either they will move in the right direction or left direction, then this spring will don't have any compression or elongation. Okay. Second, now a1 by a2 is equal to -1 means middle spring will have both compression and elongation. Okay. Let's say a1, this is my displacement of mass m1 and this is my displacement of mass a2. -1, so I have put it like this, and then this is our mode shape. Increasing linear, decreasing, and then increasing. So here we can see in some part it is elongation, some part it is compression. So it will be more clear from the diagram. Either they are moving in close to each other, it means this spring will compress. If they will go away, then this spring will be elongate. Okay. But there will be one point in the middle of a spring that will neither move. Okay, that will neither elongate nor extend. So that point I have identified at P. Okay, this point there will be no deflection in this spring. Okay, so this is our 2 degrees of freedom system. How to find out the equation and the amplitude and the omega. Okay, this was our system. What we have done, x1 by x1 is greater than x2 we have assumed. Free body diagram, then try to make equations by Newton's second law. What I have done, assume some solution like this is harmonic solution, we know x1 and x2. Putting this in the equations obtained by Newton's second law of motion, then setting determinant 0, we will get some omega. Because quadratic we will get 2 values. Then a1 by a2, as we have discussed here, a1 by a2 1 -1. What is the meaning of 1 -1? 1 means they are in phase, -1 they are out of phase. So mode of vibration is lowest, it is first mode, higher than second, and if one more is there, 3 degree of freedom, then it will be third mode of vibration. Okay. Principal mode of vibration, when they will have two masses will have same frequency and they are in phase. So omega is equal to root k by in our first mode of vibration and principal mode of vibration, and this is the mode shape. Okay, thank you. Be follow this. Okay, I will be uploading more lectures, so thank you.